Thank you. Thank you for inviting me to present this work and to be able to share a little bit my passion with you. I will be presenting two parts in this lecture. One of the first part will be introducing artificial intelligence, just to give you an idea about what is artificial intelligence and how is artificial intelligence capable of learning from experience. And then the second part will be how the application of artificial intelligence in astronomy, mainly in galactic and the stellar astrophysics. So the idea of artificial intelligence is extremely broad. And it's not recent, in fact. So the concept of having a machine thinking for us is really ancient. So here, just I wanted to show you this because I think it's interesting that, like in the mythology, the first robot was called Talos, which was the first robot made of bronze that has the purpose of protecting Europa. So this was let's say, the first way the people start to think about what if we had something automated that can do the job for us. And based on this, mainly the application of artificial intelligence wasn't able, scientists were not able to apply the technology or the artificial intelligence techniques because of the lack of technology. And the first time it happened, it was in the 50s. So the term artificial intelligence was coined by John McCarthy in 56. And the first lab in artificial intelligence was founded in 1959 at MIT. Now, John McCarthy also should know that created the first chatbot, equivalent to a chatbot called Lisp in the 50s. It was a chatbot that was capable of answering few questions. And it was, of course, extremely basic, but it was the first one. Now, nowadays, where do we see artificial intelligence? We're everywhere, especially in the last 10 years, we see it everywhere. From the first few words we start writing on Google search, the way that Google search start filling automatically what we would like to write is based on an artificial intelligence algorithm. When we call if you want to call the insurance company, there is an automation, like a voice that will start talking to us, which is based on an artificial intelligence algorithm also. The video games industry is all now based on artificial intelligence. The cleaners, the automated cleaners at home, the hoovers or the iRobots, all of these also use artificial intelligence to be more efficient. The amount of money we pay for our healthcare depends on several parameters. There is no person now who decides how much we should pay our insurance, but there are algorithms based on training, on learning, on the characteristics of each person, and decide how much you pay. When we apply for a credit card, for example, why our application is refused or accepted depend also on algorithms that take many features, many characteristics, and decide if we deserve this credit card or not. So also one of the most important application is what we call the recommender systems. Like when we buy on Amazon or any kind of online store, we receive a lot of messages that you would like maybe to buy the other item, or you would likely to buy something else, which is a recommendation, but also based on artificial intelligence. Like in Netflix also, when you watch a movie, then you would receive another recommendation. What about this movie? People who like this movie also like the other movie. So all of these are usually application of artificial intelligence. But the big boom, let's say, in artificial intelligence started in 2016 most of you maybe remember this, when the machine was able to beat Lee Sedol. Lee Sedol, for those who don't know who he is the champion of the the Go game. Go game is a game very similar to, let's say, in philosophy to chess. It's not, but I mean, the concept is a board game like chess, extremely more complex than chess. To give you an idea, the number of possible movement on the AlphaGo game is 2.1 times 10 to the power 170. So if it's like 10 with 170 possible way to move these objects on the board, which is more than the observable, more than the number of atoms in the observable universe, which means that the number of possible steps that the machine can do is very large. And to be able to play with the champion and beat the champion was something extremely amazing, because it used a technique that even the player was not able to understand at the beginning. So it was something remarkable. And nowadays, here on this slide, I show you how the evolution of this AlphaGo game happened. You will see that the AlphaGo that was able to beat the champion requires like few days of trainings, whereas after 40 days of trainings, there is another AlphaGo that is called AlphaGo 0, which is based on training by itself. It means the machine trains itself by playing the game against itself. It was able to beat all kinds of champions in this game after 40 days of training, which means that the future of these kind of techniques of artificial intelligence are surpassing the capacity of the human brain. It doesn't mean, I just want to make sure that this is clear, it doesn't mean that we won't find a person who can beat once every while the machine, but on average, the machine is able to win all the games of AlphaGo. And why AlphaGo and not the chess, like what happened with Garry Kasparov a long time ago with IBM? Because AlphaGo is extremely more complex than chess. So being able to beat Lee Sedol was extremely remarkable. Now, this is just a small introduction about the application of AI and why now we are talking a lot about AI, because it's everywhere now, it's everywhere. But we should understand that it's still a machine doing a job for us. And that's why in the definition of AI, there are two types of AI. There is something that we call the weak AI, which is the weak or the narrow AI, which is we have a machine or an algorithm that can do one specific topic, which means if I use the AlphaGo AI that plays the AlphaGo game, it cannot, for example, play chess. It's done for one purpose only. Whereas the strong AI that doesn't exist yet is an AI that can do everything, okay? That can think logically, make decision, plan, and train itself. This is, of course, a lot of projects exist to be able to make the strong AI. Putting two weak AI together cannot make a strong AI. To give you an idea what could be a strong AI, as a fan of Marvel series, the comparison with a strong AI would be Ultron. If you are familiar with this, Ultron is a pure example of a strong AI. So if you watch the Marvel movies, that one of the movies deal with the age of Ultron, and it explains how artificial intelligence was capable of taking over. And this is an example of strong AI, which means an AI with a conscious. So that's the role. That's how AI, let's say, is involved in our daily life. But the problem is that how do we train AI, and what's the relation with science? What we should know is that AI is based on data. Without data, there are no AI. Data is the most important parameter when we train any artificial intelligence algorithm. Now, the data that we put in any algorithm to be trained, we should understand that it's a data that is put in a computer then that the computer, using specific techniques, is capable of understanding what is happening. So the data is a bunch of 0 and 1, but these could be understood by the computer and can be used by the computer to train the algorithm, any kind of algorithm that is based on AI. Data exists in two ways. There are structured and unstructured data. Most of the structured data is tables, like an Excel file is a structured data. An image is an unstructured data because the representation of the pixels on the image is not well defined. An audio file is unstructured. An email is unstructured. For example, if I would like to create an algorithm that can detect from the email the mood of the person, if this person is happy, is sad, is anxious, I need to take the email and start analyzing the data in the email. So I need to put the email in an ordered way to be able to analyze the data. So an email is purely unstructured data. Whereas if I have a table with the prices of houses, for example, as a function of the number of rooms, the location, this in an Excel file, this is something that is structured. So this is a structured data. So these are the two ways to have data, and structured and unstructured. Now, mainly most of the data is unstructured. 80% of the data is unstructured. And the role of all data scientists or scientists that would like to use data to create algorithms to be able to predict whatever they want, they need to make the data from unstructured to structured, which means there is a long time of preparation of the data. This is a time-consuming phase, and we need to adapt all the techniques to be able to transform this unstructured data to structured data. That's one. Second, the unstructured data, as it's large, it requires a big database, which means it requires more storage capabilities. So we need more hard disk to store this information. So which means more complex, more time consuming, and more expensive. Structured data, on the other hand, requires less storage. It's already compact, it's already compressed, and in files that are used directly by the user. So usually the main, or let's say most of the time of a data scientist or a scientist working with data will be in preparing the unstructured data to structured. And this is also applicable when we have data from observatories or from space telescopes. The first thing we need to do is to reduce the data, to clean the data, to be able to analyze it. Now, in artificial intelligence, what do we use? We are not constructing robots. We are constructing mainly algorithms that can use the data from our telescopes for all kinds of astronomical data. So what we use, in fact, is a branch of artificial intelligence that we call machine learning. Machine learning is just a technical way to say we are using mathematical function and algorithm that are able to use the data to predict some output. So we use complex data in order to predict whatever we want from this project. Example, if I have a picture and I want to know if this is a galaxy or this is a star or this is a supernova or this is a planetary nebulae, I need to take this data, do a kind of learning on it, and then try to predict what could be the output from it. And this is done using statistical tools, and these statistical tools are based on mathematics. So in fact, machine learning and deep learning, which is a branch also of machine learning that deals with the neural networks that I will be talking about in a moment, these techniques use complex mathematical techniques to infer any kind of output or whatever we want from our algorithm using a data and using a training process. Now, why do we need this? Why can't we base this on human? Why can't we, as scientists, take the data and do the analysis without the use of computer? Other than it's time consuming, what we can do now, I will talk about my personal project, what I can do with the machine learning now in 1 hour. I couldn't do this in, let's say, for a period of 10 years when I was doing my PhD, which is like around 15 years ago. So the time consuming, or the time that we need to process data, is important. But other than this, which is more important, is that the capability of the machine is better than a human. What you see here is a way to represent the accuracy of the model as a function of the amount of data. So if the amount of data is increasing, like you see here on to the right, the performance of our models improve by moving from conventional machine learning until we reach deep neural network, which are based on also mathematical techniques, but mainly a little bit different. And they surpass the human level performance. So not only we are gaining in time, but also we are gaining in performance. So not only I can do faster, but I can do faster and better. And that's extremely important, because we cannot use like hundreds of PhD students on a topic and hope that we will have better results than a good algorithm that is capable of surpassing these predictions based on the human studies. So that's why you will hear a lot of in artificial intelligence is that the data is the new oil, because we use data to do that. We use that data to do everything. So how do we use data? What is the step to do that when we have data? And remember here, the data is not necessarily applicable to astronomy. It could be any data. There are few techniques in artificial intelligence, as I said. So you have to think that artificial intelligence is the umbrella over all the mathematical techniques. One of them is called machine learning, which uses statistical tools. And in machine learning, we have a more complex tool called deep learning. But I will call them all machine learning. And these machine learning are divided mainly in two steps, mainly in two big groups. There is a machine learning that is called a supervised learning, and there is a machine learning technique that is called unsupervised learning. So I'll take a few moments here to explain the main difference between these two. A supervised learning is that I have pictures of dogs and the picture of cats, and I tell the machine, this is a dog and this is a cat. So I let the machine train on images of this is a dog and this is a cat. And later on, when I bring an unknown picture that I don't know if it's a dog or it's a cat, I give it to the machine. Based on the training, the algorithm will tell me this is or a dog or a cat, but it will tell me one of these two because it's supervised. I told the machine that your only two options are dog or cat. That's what we call supervised learning. And in supervised learning, we can do a lot of things. We can classify, like the example I just gave, dog, cat, or we can regress, which means I can predict a number from a series of input. Example, I give the machine the prices of houses in New York based on the location, based on the number of rooms, number of bathrooms, and then I let the machine learn, and later on I bring a new house that the machine never saw before, and I ask the machine, according to what you learned, what could be the prediction of the price of this house based on the number of room that I will give it and the number of bathroom and the location, etc. So it will use whatever it learned to give me a number, not to give me a class, dog or cat. It will give me a number. And that's what we call a regression. So supervised learning is extremely important. The other group of unsupervised learning is mainly used to classify or to cluster, which means I give the machine, let's say, images of circles and images of triangles, and I tell the machine, please try to group these elements. And the machine will say, I have found similarities of these groups and they are all together, but the machine doesn't know if it's a circle or a square or a triangle. It just finds similarity. So it will group the circle together and it will group these squares together without knowing what are these two. So it's unsupervised. So I didn't tell the machine that these are circles and these are triangle or squares, sorry. So I just gave the machine picture and the machine is able of classifying them. That's what we call unsupervised. And these are mainly the two big domain in machine learning, the supervised and unsupervised. The last one that is used a lot, but not in astronomy, in fact, is what we call sorry, where is it? Here is what we call the reinforced learning. So the reinforced learning is a type of learning that work by experience. I give an award for it. So when the machine is doing a kind of step, when it's doing steps in the calculation, at each moment the machine will notice that, no, here I did a mistake, and it's not a reward, it's a punishment. So we give the machine some kind of hints about punishment and reward, and we let the machine learn by experience. It will teach itself to do that. It's beyond what I wanted to explain today. It's a little bit complex to say it in one slide, but it's what we call reinforced learning. It's used a lot in video games. It's used a lot in board games, automated board games. So that's mainly the word of the machine learning and the techniques of supervised and unsupervised. So that's why the next slide I will show you is a summary, which would be interesting in case you would like to keep this presentation with you, where it summarizes all types of steps that we use or all types of machine learning techniques. And don't forget, machine learning is just a subgroup of artificial intelligence. So this slide and the next slide just explains how is the world of artificial intelligence and what we can put in it. So this is a machine learning technique divided in supervised, unsupervised, and the small part reinforced learning that is under the umbrella of artificial intelligence. Also, for those who are interested in to know the epoch when these techniques were used, here in this slide you see the time and the years of the where we were able to apply these techniques. Artificial intelligence is old, as I said, since the 50s, but with the increase of the computational power, we were able to use more complex mathematical tools, and that's why we were able to do machine learning in the 90s and I mean 20 years ago. And now with more complex and more performant computer, we can do what we call neural network. And neural network are the, let's say, the babies of deep learning. So what are these neural network and these deep learning techniques? So in fact, these neural networks and deep learning, they try to mimic the behavior of the brain. How? Well, you have to suppose that this is a cell. And of course, these techniques want to mimic the behavior of the brain in a computer, which means using 0 and 1s, which means using mathematical tools. So how it works, in fact, in few words, is that you have an information that will go into what we call a neuron. The scientific way to name this neuron, this cell, is a perceptron. The perceptron is the representation of a neuron in computer term. So this perceptron requires an input, and once it takes the input, it does its work, or what we call it activates, and then you have an output. An example of this: I observe. When I observe, that's the input. My eyes and the brain activate. The output, it's a dog. I observe another animal, activation, the output, it's a cat. So that's what the network try to do. And it's a technique that is extremely computational consuming in terms of computational power. So it started with one neuron, one perceptron. The first example started with one perceptron in 57. In 57, they started with one perceptron trying to characterize two types of animals, dog and a cat. And in this perceptron, this perceptron was able to make a line separating a group of cats and a group of dogs. It was extremely useful, only with one perceptron. It was a very small data set, but it was able, using some features, to characterize dogs and cats. It was the first time perceptrons were able to give a result in classification. This is, of course, a classification scheme. So that's something extremely revolutionary, and it wasn't used a lot. The idea is old, but it wasn't used a lot because it requires a lot of computational power, and we didn't have this computational power to do this. One way to see this is the analogy between the computer and the brain. Of course, this is not scientifically correct, but it's just an analogy to represent the brain with a microprocessor. So which is what the neuron size, the transistor, how much energy is used for a brain to characterize a cat, and how much the computer requires energy to characterize a cat. I like to put this just for a comparison. It has no scientific value. It's just comparing the brain to a computer, and that's what usually deep learning trying to do, is to to create a kind of network that is capable of mimicking the behavior of the brain. So in another way, you have input and you have a set of neurons and you have an output. Like exactly the same thing happened with our brain. You have an input from the eye, for example. It could be from the touch, and neurons are activated, and you have an output that is a cat. We do exactly the same. And of course, more complex, or more the number of neurons that we put in our algorithm, more complexity of the algorithm will be, more big the network will be, and more calculation time is required. And this has been used a lot until recently. We were able to apply all of these, but now to images. So not only to images, not in a way of having characteristics of the animal. In the example of cat and dog, previously it was like giving characteristics of the dog. For example, the size of the head, the number of, I don't know, the color. So we were putting itemized. Now we give just a picture, and that's it. And the code is capable of doing everything. This is this revolution in giving images instead of numbers have changed everything, because of a new type of network. It's also in the neural network, but called convolutional neural network, CNN, convolutional neural network. It's based exactly the same as neural network, but with kind of filters. So example, you give an image here. This is an image of a zebra, for example. You apply these filters. Okay, you apply these filters, and the output will be a probability for each category of your animal. For example, if my training data contains 100 animals, I will have the probability of each category. And if I'm observing a zebra, for example, you will notice that the output will give the maximum probability for a zebra. And like this, the user will know, what I'm observing is a zebra. This is what is called a convolutional neural network, used a lot in deep learning, and extremely powerful tool, because it gives a lot of better performance than any classical neural networks. So that was a small summary about what kind of tools we will be using in astronomy, and that I will explain later in the part related to the astronomical application. So to repeat this, I have the word of artificial intelligence that contains another world of machine learning based on mathematics and statistics. And one part of it, the small part of machine learning, is what we call deep learning, that contain the way of solving problems using a neural network. And mainly, most of the application of artificial intelligence in astronomy are based on these neural networks. Now, one thing to remember before I finish this first part is that training the data, you should think about it as training a kid. What does it mean? It means that the kid usually think like their parents, which means if I am a parent, I teach my kids that this is wrong, this is right. My child will always think that this is right, this is wrong, wrong, this is right, based on how I train the algorithm, how I train my kid. So it's very important to know if there is a bias in my training data set, there will be a bias in the output. Okay, so if I train with wrong data, the output will be wrong. So it's very important to make the data unbiased. It's one of the most important things. So now I will show you a few images just for fun to show you how we trick models, how we trick the codes. That's one example of it. We give images and for a code that is not really trained a lot, and the code is not capable of differentiating between which of these is a muffin and which of these is a dog. So that's something that we could, like, based on these kind of results, we can trick the code and see where are the issues and how to better train to do this. Some other pictures also that are funny. This one, where you can also train the code to see an animal or food. Of course, here one of them is extremely tasty, one of them is cute. So it's very important to know which one is which. So we have a lot of these kind of things where we have to make sure that the code doesn't make a lot of mistakes when we do this. So the training data set should be large enough to take into account all of these. Another one that is also interesting is this one, which is also you can train the code to better learn and better give you better results. So one also interesting fact about, or one issue with the learning, is that I was talking about the recommendation system previously, which is sometimes it can be a little bit annoying, because if we buy on Amazon, an example, if we buy a pen, Amazon will continue sending us messages about there is a new pen, or there is something similar to what you bought, and if you are interested in buying it. But if I buy a house, usually people who buy houses won't buy another one after, like, I don't know, 15 years on average, especially if you are in academia, which will be one house and that's it. But if you will always be receiving emails about, or recommendations about new houses, and what about buying this house or this house, because this is an automated system based on recommendation independently of the product. So here it's also a funny picture where customer who bought the left side of the shoe also bought the right side, which is something always happens, but the recommendation system doesn't know the human part of this or the logical part of this. So it will always give you some kind of recommendation that are not interesting for us. So that's the part related to artificial intelligence. I can talk a lot about it. It's a field that I really like. But I mean, that's what I want you to know for this continuity of this presentation. And now I will pass to astronomy. So why do we use it in astronomy? Why is it interesting now to use artificial intelligence in astronomy? Well, because of the data, of the amount of data. Just as you know, and for sure, I mean, most of you attended a lot of presentations in astronomy, know that the amount of data we have in astronomy cannot be represented in any way for the human mind. I mean, only in our galaxy we have 200 billion star, and around every star probably there are a lot of planets, and on every planet there is an atmosphere or not with these molecules or not. So in order to analyze all this data that we are receiving every day from all the telescopes and also from all the galaxies, if we are observing the observable universe with all the multiple billions of galaxies with billions of stars in each galaxy, it's impossible to do this without automation and without good classification, good analysis, performant analysis, accurate analysis. And when we say a lot of data with fast techniques and accurate and performance and good precision, we have to pass through artificial intelligence now, or we have to pass through deep learning or machine learning. So that's the first use of machine learning or of deep learning in astronomy. This was done in '92. It was one of the first, let's say, artificial neural network, which is not convolutional, by the way. It's a normal neural network that didn't use photo, use numbers, that was based to classify galaxies. It was very useful. We were able to classify a lot of galaxies with this, still used. I mean, it was very performant. It was able to classify galaxies. Sorry, I need to go back here. Just for those who are familiar, the classification of galaxies is based on the Hubble classification scheme. This is based on the Hubble classification scheme. We can classify that this is a spiral galaxy, this is a irregular galaxy, this is elliptical galaxy, and we still use these techniques now. In fact, we still use these techniques now, but of course with more performant techniques, with more performant algorithm, with more performant neural network, mainly convolutional neural network that can classify the galaxy and see if the galaxy is a spiral or not, if the galaxy has bars or not. So as an example here, I will show you the three types of galaxies. You have the spiral galaxy, the elliptical galaxy, and irregular galaxy. So it's able to classify these, to put them in groups, and to give us as an output if this is a galaxy or not. This is not recent, but because of the large number of galaxies we are using it, we have to apply it in an automated way. And now, of course, some scientists use this and then make a check on them, but the code or the algorithm is already extremely performant to do this. And nowadays we have more than around 720 million classification. So this is called the Zooniverse, which is based on, of course, artificial intelligence, but also with the help of users. So that's something interesting where there is no way to skip the part of artificial intelligence. We have to use automated techniques here. Another application also is the exoplanet detection. As you know, most of stars have planets surrounding them. There are a lot of techniques to detect exoplanets. One of these techniques is based on light curve, which is the increase of the amount of light coming from the star when the planet passes in front of the star in the line of sight of the observer here on Earth, or on the line of sight of the telescope. And you have a small dip in the light curve. Now, what happens is that this is a time-dependent phenomenon, which means we have to observe for a specific amount of time to see the dip, to see when the planet passes through the star, and you see the dip in the light of or the decrease of the brightness of the star due to this planet. But as we know, stars are big, planets are small usually, and this decrease is extremely small, which means that sometimes we cannot distinguish between the noise of our instrument and if this decrease of the intensity is real or just an artifact from the instrument, or just coming from the for the non-capability of the user to be able to see that this is really a dip or just a problem in the data reduction. So for that reason, we train machines, we train algorithms to classify these as, yes, this decrease is due to an exoplanet, or no, this decrease is due to something else. So we do it in an automated way, and a large number of exoplanets were detected like this. So this is called a time series analysis because it requires time. So it's an observation with time that requires a lot of, the several observation to be able to detect the dip or the decrease of the light of the star using artificial intelligence. One of the most important telescope now, which is a US telescope that was launched in 2018, is called the TESS, the Transiting Exoplanet Survey Satellite, uses the light curve technique to detect exoplanet. Of course, the light curve technique is not the only technique to detect exoplanet. There are many others, mainly another technique called radial velocity technique that requires the use of also artificial intelligence. But light curve is very useful for time series analysis, and it's like being used a lot now to derive, let's say, to detect if this is an exoplanet or not. And it can reach 96% accuracy, which is a very good number. But once the detection is done, can we have an information about the atmosphere of the star, of the planet? We are interested in knowing what's happening in the atmosphere. So what we do is also we create a kind of simulated data, and we train the algorithm to understand what are the molecules in this simulated data that could be used later on to be applied on our true observations from our telescope. So we train the machine to know this is ammonia, this is titanium oxide, etc. And then the machine can use the information coming from the telescope to derive the composition of the exoplanet atmosphere. And that's one of the projects is called the robotic exoplanet recognition, which uses these techniques to derive to identify molecules in the atmospheres of exoplanets, molecule like water vapor, H2O, like carbon dioxide and others. So it's extremely useful, and it's used a lot now to derive these kind of molecules in the atmosphere. And that's, I mean, the use of why do we need this depends on the project of every scientist. What I'm talking here about is the technique and the tool, not about the project itself. The project could have different goals. I mean, one of the goals is to see if life can be found on these exoplanets. Other goals is to do a kind of statistical overview. So the scientific goal is not what I'm talking about here. I'm talking mainly about the technique. Another satellite that is also using this technique is a satellite on which I worked when I was doing my postdoctoral studies in Spain, is the Gaia satellite. This is a satellite that uses the role of it is to make a 3D map of the galaxy, but not all. 3D map means that we need to know the distance of all the objects, and we need to know not only the distance, but also the characteristics of the stars. And this is done usually by using algorithm such as the artificial intelligence algorithm to make the detection more accurate. Gaia will detect will be observing mainly 1% of the galaxy, which is a huge number. I mean, 1% of the galaxy is more than 1 billion star. So it's a lot. Now, other places also where we can find this is the famous gravitational waves. Now, gravitational waves are physical phenomena that appear when you have extremely dense objects falling around or rotating around each other and colliding or falling inwards one on the other. These big objects could be could be or neutron stars usually because they are extremely dense, or black holes. So we could have black holes colliding, we could have neutron stars colliding, and when they do, they emit gravitational waves. And gravitational waves in the last few years were extremely studied because it requires a new type of thinking and a new kind of telescopes. I mean, we don't need a light telescope anymore. We need other types of telescopes. So it's a new astronomy that is being studied a lot. And these gravitational waves detectors, the most famous ones are the LIGO and Virgo. and have detected several ones. And it's using machine learning. So it has detected more than 10 gravitational wave detections, and using purely algorithms based on machine learning, because it's so complicated, it's so, let's say, sensitive to any kind of variation. Because the gravitational waves effect on Earth is minuscule, is extremely small. So in order to make sure that we are detecting a gravitational wave and not an earthquake, I don't know where, or someone walking really close to us, it's important to have good models, and the models are using machine learning. So that's the gravitational wave. It's a topic that is extremely interesting. Another topic also where we use this is the gravitational lenses. Gravitational lenses are phenomena where you have the light coming from star is increased in terms of brightness due to a big object between us and this star. I'm talking about star, but it could be a galaxy or any bright celestial object. So the light coming from this celestial object is increased due to the fact that there is a big object in between us and this celestial object, acting like a lens. And this is something that it's understood due to the to the general relativity of Einstein. We know it well, we know how it works, and it can create a kind of lens and increasing the brightness. Now, how to detect these gravitational lenses? You can see here one. Here you see this, that the object are distorted. These are in fact galaxies, that the light coming from the galaxy is distorted, like there is a lens between us and the galaxy, and that's because there is a massive object between us and the galaxy that is doing this. So this gravitational lens finding is based on artificial intelligence and also an algorithm that can detect that this is really a gravitational lens, not an artifact. So in fact, it was being noticed that the challenge, there was a challenge, sorry, here I forgot to tell you that there was a strong gravitational lens finding challenge that was used that was launched in 2018 for astronomers to find what's the best tool to detect gravitational lenses, and the best tool was a convolutional neural network. So as I said, these models were better than people because, as I told you before, when you have a lot of data, you need something automated, and mainly deep learning, more precisely convolutional neural network. So to go back now from the biggest part to our to our neighborhood, which is the solar system, the sun. So the sun is analyzed a lot and nowadays using artificial neural network. Why is that? Because as you may know, the sun is an active star. It emits a lot of radiation and it emits a lot of flares, and it has a cycle of 11 years, and every 11 years the sun the sun magnetic field switches, and when it does, it emits flares in our direction, the solar flares in the solar system. And if they are in our direction and received by Earth, we see what these aurora borealis, or the northern light on Earth, and especially in the Nordic countries, I mean, in the high latitude countries. So the solar flares, and to be able to understand the solar flares or the intensity of these solar flares, there is a kind of indicator which is on the sun. During the high activity phase of the sun, we see sunspots on the sun. We see mainly at the latitude, at 30 degrees latitude, and then they go to the equator. And the number of sunspots was monitored since Galileo. Galileo was the first one to observe the sunspots, in fact, and to confirm that the sun is a rotating star. So the number of sunspots is observed since, like in this figure here, in this figure that you see, the below one is the number of sunspots as a function of the time. And now, and every 11 years, you have a peak in the sunspot where the sun is extremely active and then a decrease. And now we are in 2023, so there will be a new peak here. It's very hard to predict how many sunspots we will see and what will be the activity of the sun. That's something that we cannot predict. Nowadays, models using time series are capable of predicting this. And models that are complicated, models that use a neural network combined with time series analysis. These are specific neural network, specific deep learning techniques, neural network that require a time series analysis. One of these models called LSTM. The LSTM stands for long short-term memory. So these are convolutional neural network that are based on a time series that are capable of predicting what could be the next step, the next behavior, knowing the previous behaviors. I'm not saying these are really accurate model, but we are trying to use them. They have been used a lot in techniques to predict the stock market. But of course, they failed miserably because the stock market could depend on extremely large parameters. So the sun, I think, is still simpler than the stock market. Anyway, so the prediction for the next, according to the next solar cycle number 25, that will happen now, in fact, in 2024-25, this model, the best model for now, predicts the yellow curve that you see here on the screen. So these are the models. This is the model that predicts what could be the solar cycle. So it seems it's not really a very active cycle, very similar to the one we saw in 2012-13. If you remember, it was in 2012 when we had this idea of the end of the world and that the sun could emit a lot of radiation, burning whatever is, destroying Earth, but it wasn't the case. So the cycle number 25 will be something extremely similar, very smooth cycle. But I would like to insist here on the fact that this is not extremely accurate. The LSTM model, the models that use time series are not really extremely functioning properly, especially for complex problems like the solar activity. Okay, robots on the planets also uses artificial intelligence. Why is that? Because if there is a problem on the robot, it's very hard to send a rescue mission or send someone to fix it. So what we usually do is that we make the robot mainly complex enough. We put it a complex algorithm that is trying to correct itself if there is a problem, trying to fix its own obstacles. So this is done using a very complex algorithm, using robotics, which is an application of AI also that is trained on examples that we did here on Earth before launching the robot or before making the robot go to space. So these are something really important that we do. The rovers on planets is extremely complex, especially if there is a problem. When we can't fix it, that's it. Impossible to repair it. Except sending a mission, which is extremely expensive just to repair a robot. So sometimes it's cheaper to make another one and send it again. So that's a very important application. It's in fact very similar to the application of automation here on Earth, like what's happening with the Tesla cars, that they use a lot of artificial intelligence tools to drive without the help of a human. One other application, which is the assistant and robots for people in space. So let's suppose you have people in the International Space Station or in a mission, in a long-term mission in space. There are a lot of projects that are trying to make robot taking the role of not doctors, but like support. For example, if an astronomer has a health issue, so the robot can use whatever it learns here from the medical part and from the human part on Earth to be able to act as a mental health how do we call it, helper, or not a psychologist, but something similar to that. So these are like projects that exist, of course. Also the way of when you have several, like a crew of multi nationalities, so sometimes it's not simple to communicate. Of course they all speak English, but I mean sometimes you have, for a reason, someone cannot express properly. So there is a branching of artificial intelligence called NLP, which stands for natural language processing, sorry, neural language processing, that requires that try to understand from the sentiment analysis of the person, what is this person trying to say. This is a theoretical field, especially for the future, where we will be sending missions far away to long distances, like to Mars, or even further. Okay, so these are interesting. But nowadays there are kind of application for the crew on the ISS, where they can use some kind of software to see if to check if the gloves are okay or not. So this is usually done by Microsoft. This is done by Microsoft, that can detect the shape and the stage of the issues that happens on the glove. So it's something very interesting that is used, because I mean sometimes it's easier to use it to let the machine do this job than to remove the gloves and make sure that everything is okay. So the machine can do it automatically, really fast and more accurate. So that's something extremely important. Another way similar to what we use in GPS, there is also a way to use it in planets. So with the Intel is having, of course, with the help of NASA, to develop a navigation system of the moon, which is interesting. Like you were talking previously before we started about like having a time, universal time, not only for Earth, but also between Earth and the moon. So maybe we'll have a GPS between Earth and the moon one day. Finally, there are a lot of algorithms now that can study from the satellites. So that now I went really to Earth, to satellites that can take millions of pictures and in a few seconds analyze everything in real time, using also artificial intelligence and mainly convolutional neural network to see if there are issues or not. Now, I know I mean I have a lot of examples, but I tried to pass really fast on them. Would like to end with an example with my personal study, just to give you an idea of what I do with all of these. Is that I'm an observational astronomer. I use a spectroscopy, which is light coming from stars. I divide it according to frequency, and I use artificial intelligence to be able to see this, what we call a spectrum, which is the different intensity as a function of frequency, to derive parameters such as the temperature of the star, the gravity of the star, the rotation of the star, the content and metal of the star, and many other parameters. Because what we receive from Earth, from the star, is a combination of all these parameters. And I use now, these are spectra of different stars, and what I'm trying to show you here is that if you change one or two parameters, the whole shape of the intensity as a function of the wavelength or as a function of frequency changes. So what I do is that I train a convolutional neural network based on synthetic data to be able to characterize. So I put different layers and different neurons to be able to characterize these stars based on a synthetic data, and then I apply this to data coming from stars. So once I have trained the code or the algorithm, I apply this to real stars, and I'm able to derive accurate value for these stars. This is mainly what I've been doing in the last few years in the application of artificial intelligence. And this is what I will continue doing, continue investigating with my students in the next years also. So I would like to conclude this presentation. I know it is a lot of things, and I hope just you enjoyed few ideas about it. You should know that the machine learning and mainly AI will transform everything based on, because of the amount of data we have, and the amount of data is increasing. It's always increasing. It will never decrease. It will become more complex, and we will be using artificial intelligence to take and to have some insight about the important parameters of all this data, all this amount of data. If we need to know few things from it, how can these artificial intelligence take what we really need from it, and not use all the data and use a lot of time to be able to take whatever output we need from these data. And the use of human will always be needed. That's something extremely important to keep in mind. The future most probably will contain a collaboration of human and AI together to improve other than what we do now with robotics, but also in terms of algorithm to do this. What I did something yesterday. I had the idea of asking ChatGPT, which is the new famous AI search engine that you have on the web now, which is free, which is based purely on AI. Ask ChatGPT, what do you think about the future of AI? And here I put some of the results that I got. I think it's interesting to share with you this. One of them is that AI is expected to continue to evolve and impact virtual. So it's an AI that is telling me what it thinks about itself. So that's how you should think about it. That machine learning will learn from data and improve their performance over time. And we will have more powerful, more sophisticated AI in order to be able to solve tasks with greater accuracy and with higher efficiency. Growing use of AI in decision-making also processes, which means assisting a human decision to make the decision more automated. And there would be, of course, some issue like in privacy bias and job displacement will need to be addressed for sure in order to ensure that the benefits of AI are realized by everyone. This is an AI giving its opinion about AI. It's not my opinion. This is not my conclusions. This is the AI conclusion. And finally, I would like to end with this slide. These are few sentences about the what let's say famous people think about AI. Famous and or rich people think about AI, and of course these are just their thoughts. They don't it doesn't mean these are what they say is true or not, but this is what they think about AI. Mainly that what Elon Musk thinks about AI, that is a demon that is potentially more dangerous than nuclear weapon. But after all, it's Elon Musk, so who knows if it's really what he thinks or not. So anyway,
it's more dangerous than Elon Musk.
I didn't say that, but yeah. So yeah, with this I would like to end. Thank you for listening to my presentation, and sorry if my accent wasn't really good, or you were not able to understand everything I said. And if you have any question, I really will be happy to answer you. So do you want me to stop sharing the screen, or?
Yeah, we're going to have some questions. Yeah, thanks for making such a complex subject so clear. I've sat through so many AI lectures, and usually I'm like, wow, really good, very clear. Let's see, do we have anybody either in the audience or on the Zoom? On Zoom, you can either raise your hand or just yell out in the chat. Let's see, okay, let's see what's in the chat here. So, these are some.
Yeah, I found a question on the chat, if I may.
Yeah.
Yeah, there's a question about the GAN. Someone asked about, I talked about CNN, but are GANs used in astronomy? This is extremely, GANs stands for generative adversary networks. It's a way, I think that's what GAN means, but GAN are like, if you have seen on the web pictures of people that don't exist, or GANs are like algorithm based on neural network. They are purely neural networks that can create images from previous images. But the images of people, for example, if I train the model to create if I train the model on images of faces of people, it can be able to draw images of faces that don't exist, the people don't exist. So it's like to increase the amount of data applied for any kind of network. Now, is this used in astronomy? Not to my knowledge. Is it useful? Yes, it could be useful. It could be useful for one thing. There is a technique that we use in artificial intelligence. It is called data augmentation. Data augmentation is a way to increase the amount of data artificially to make our codes more efficient. So one way to increase the amount of data is to use GAN. That's one way of doing it, especially if there are images. But GAN is a very recent technique. It's a very recent topic in artificial intelligence, and it's a recent topic in neural network that is used a lot to create images from real images. So one example also for GAN is that there are applications now where you draw me, I don't know, Super Mario underwater. It will draw a picture of Super Mario underwater and things like that based on what we write in the chat box. And this is based on GAN. It uses whatever it learned before to apply it to new images. So it's creating fake images from previous true images. It can be used in astronomy if we need to augment the data.
We have a couple more in the chat. Are we building the chips we need for AI?
She's reading the chat questions.
Are we building the chips we need? That's very hard. That's a very, in fact, are we building models to go with the chips we are building? It's more the reverse how I see it, is that now we have these performance, where we can go to the limit of our network, of our algorithm, to be able to use the whole performance of the chips. So the chips are not the idea. There is a law, a very famous law called the Moore's law, which tells us a little bit about how technology will evolve with time. So we are limited in terms of technology of how much chip we can put in one computer and the size of the chip. But what we are doing now is that whatever the technology is moving, the industry is capable of building, we are improving our models to be able to use the full power of these chips. That's how we are doing it. We are not doing the reverse.
Somebody's asking, are there any reference code repositories with examples of AI applications for astronomy?
Well, unfortunately, it's very hard to find. So whatever I explained today is based on scientific papers that I read in relation with AI and try to summarize them. It's very hard to find a repository with application where people can use. Mainly, if you are familiar with a platform called GitHub, where computer scientists and scientists put their work there. Some of them are astronomy-based work. So you can go download the data set, download the codes, and try to play with these codes to see how you can use this data set. But you should know that the coding is necessary, which means that you should be able to understand a little bit of coding to be able to do that. So coding is something really important in AI. So to be able to apply these astronomical tools, we need to be familiar a little bit with coding, and mainly with a language called Python. Nowadays, we use it a lot, Python.
Yeah, so now we're starting to get a lot of questions. Are you using any techniques for your neural networks to understand why the system comes up with the answers? regarding explainability.
I don't know if you mean explanatory AI or not. I'm not sure what what's the question. But what we can do is that while we are training, I mean, I trained the model on data that I created, which means I know that what is the output that I should have. So that's what I explained at the beginning, called supervised AI. So I trained the model on data that I know what I should expect to have. And once I do that, I train it for a long time until I reach the accuracy that I think it's enough for whatever scientific project I'm doing. So for example, if I'm training the model on billions of stars that I created their spectra, which are synthetic, not real stars, and I find the accuracy of 96%, then I apply it on observation that I know what should expect on well-known stars, and I still find the same accuracy. I can say that my code, my algorithm is capable of finding 96% accuracy for temperature. So there are different steps. There is a step of training, there is a step of validating, and there is a step of application to new data. So that's how we can relate it. Now, the complexity of it is that mathematically it's impossible to do it in an equation. That's why it's using neurons. So it's very hard to understand how the steps are happening to be able to retrieve this fraction. As I'm not a computer scientist, and so I don't study the step-by-step mathematical calculation. What I care about is the input and the output. So it's very hard to be able to follow every step and to try to explain why this step is important. To make it easier to explain, it's better to use images, because we can see how the images is being filtered and what are the components that are giving the output. So it's a little bit like complex and depends on the project, but usually to explain all the steps of an algorithm is something not trivial at all.
And I think we'll take one last question. Do you want to comment on the news item about the two AI computers that began speaking to each other beyond the scientist's input a few years ago?
Sorry, can you repeat the question?
Oh, it's about a news item that there were two AI computers that started speaking to each other without the scientist's input a few years ago. Maybe you're not familiar.
You like reading the onion, I don't know.
I think this gets into, them getting past us and not needing us and ultimately taking us over.
The first, a long time ago, there is a scientist called Alan Turing, who imagined a problem called the Turing problem that can explain if a computer is intelligent or not by saying that I put in a room a computer and a person, and then in the other room a person, and this person in the other room alone try to ask questions and receives answer from a computer and from a person. And the idea is that this computer becomes intelligent when you ask a question, you are not capable of distinguishing if the answer is coming from a person or from a computer. Now, what's happening is that just by trying to how artificial intelligence has evolved, currently, if you go and ask ChatGPT about any question, you will have a feeling that what you are being answered is like a person is writing you the answer, because it's extremely totally different. I mean, you feel that the way of the accuracy in the answers and how things have evolved in the last few years is amazing. I mean, it's like there will be a time where computer will be talking to another computer and learn from themselves, so every computer will teach the other computer what the other computer doesn't know. So it's something extremely interesting. I'm extremely curious to see how this will evolve, and of course there will be some loopholes somewhere, but I mean, I'm really curious to see how things will evolve in terms of AI, and how much can we go, how far away we can go with that before having a feeling that we went too far, maybe. So it's interesting to think about it.
Okay, thank you again. Yes. I was wondering when Eli was gonna speak up. We have Eli is our youngest member who usually asks questions. Okay.
I was gonna ask, how does AI support the James Webb Space Telescope, and what instruments on the James Webb Space Telescope could we classify as AI?
I don't know if you've heard that. Eli's asking, how is AI supporting the James Webb Telescope, and what instruments on the James Webb could be considered AI?
So in fact, in all telescopes, now you have two types of AI. You have the AI on board of the telescope, which means correcting the orientation of the telescope if there is an issue, correcting the cameras, the field of view. And you have the second AI that is used on Earth, which is once we receive the data from the telescope, we try to analyze the data. So the AI is used in two ways. One, in the telescope part, which is if there is an issue with the orientation, it corrects itself. Second, once we receive the data on Earth, we use AI to analyze the data. So all telescopes now, all of them, the data analysis is mainly based on AI. So we use them everywhere. So now without AI, the amount of data that we are receiving, it's impossible for us to analyze them all. We need something automated. But not only automated, we need something efficient. So we need to use AI algorithms. So yes, you're totally right. Everywhere is now, we are finding AI everywhere in all observatories, on Earth, on ground, or in space.
Okay, thank you. Thanks so much for
Thank you all.
Oh, great.
Thank you.
A winner. Okay, thank you, Marwan. I really appreciate.
You're
Excellent
most
talk.
welcome. You're most welcome. Thank you. Thank you.
Let's hope that our papers in the future are written by astronomers and not by ChatGPT.
Hopefully.
Okay, good night.
Thank you. Good night. Have a good night.